Hi, my name is Alan, and this is my project, which is called Computer Vision Lip Reading. So, in introduction, what's the problem at hand? Over 1.5 billion people annually suffer from hearing loss. And of those 1.5 billion people, around 430 million people are deaf or hard of hearing. Over 11% of adults in the US alone could benefit from using hearing aids. So, what causes hearing loss? Well, hearing loss is mainly caused by two main reasons, which is aging and exposure to loud noises. And earbuds and headphones have increased the prevalence of hearing loss as well. And as more and more people use earbuds and headphones, more and more people will suffer from hearing loss. And this is depicted in the graph to the right, which projects the number of people with disabled hearing loss worldwide in future years. So my proposal is to use computer vision and deep learning to create an algorithm that can translate lip movements into words to help the deaf or hard of hearing. So an overview of the project to begin with. To classify lip movements into words, we use 3D convolutional neural networks, or CNNs for short. 3D CNNs work essentially the same way as a 2D CNN does, but instead of applying convolutions to 2D space, we do it in 3D space. And this is possible because of the data we're working with. The data for 3D CNN is usually video feed data, and videos are basically just sequences of frames, so we can take and extrapolate the convolutions in 3D space. So the words that I chose to train my 3D CNN on is from these 13 words that are: here is a demo, can you read my lips, cat, dog, hello, bye. So the steps for my project include first collecting data from myself and a friend. Then we process the data. Afterwards, we train and evaluate the models, and then we test the model in real time. So before I get into the technical details, let's start off with a demo to showcase my finalized project. And to note, inside this demo, I do speak slowly and with more exaggerated lip movements so that my model can pick up on the details and predict better. Mom. Lips. So as you can see in this demo alone, that my model does work pretty well and it's pretty accurate. Not only that, it can also predict pretty fast, which is good, but it's not 100% accurate, and this is what we'll see in the next demo. Cat, dog, hello, bye, bye. So in this demo, as you can see, it misclassified my as by. And if you think about it, the lip movements between my and by are actually very similar, which makes sense that the model misclassified the two. And I purposely chose to include words that are visually movement similar inside my dataset. And this includes like hello, demo, cat, can, my, and by. All right, moving on to the data collection. So there were no suitable datasets online, so I had to resort to making my own from myself and a friend. The model is personalized in the sense that it might not be able to generalize as well to new people's faces. Inside the data collection, we use transfer learning, and the model we use in this case is the DLib facial landmarks model. And what this model basically does it assigns indices and points landmarks to a person's face, and we can use these indices for segmenting out lips, seeing where the lips are, the mouth, the upper lip, etc. And basically, to collect data, I wrote a script, and this is how the script works. First, we detect if someone's talking, and the simplest way I did this was just to calculate the distance between the upper lip and lower lip. If someone is talking, then we can start recording or saving the frames. They can briefly close their lips, which indicates that they aren't talking, but as long as it doesn't exceed a certain threshold, let's say 10 frames, then we keep recording. However, if they close their lips for more than 10 frames, then we stop recording and assume that the word has finished being uttered. After they finish talking, we can pad the current saved frames with previous frames and after frames. So previous frames are just the frames that the person start with before we start actually saving the frames, and the after frames are the frames saved after the person closes their lips. So by saving these previous and after frames, we get the start to finish movement of a word, and then we get 22 frames total. Here's a demo of me collecting data just to showcase how the script works. Yeah, so as you can see from my usage, the script does seem to do a good job, but it was definitely very time consuming to collect all the data that I needed. And I think in the end, it took around 4 hours total. So now let's talk about data processing. And as we all know, data processing or image processing can definitely improve model metrics and reduce training time and resource usage. So it's definitely a very important step. And here is what I did for my processing. First, we segment out the lips because that's exactly what we care about. And to do this, we can use a dlib model to just save the mouth portion by splicing out the pixels where the mouth landmarks are at, with some padding on the sides, of course. Following that, we can add Gaussian blurring, which is basically applying a Gaussian filter throughout the image to blur edges and soften sharp curves. This will reduce detail of the image, but at the same time, it reduces overfitting as well. Then we stretch contrast. Basically, we enhance contrast to make the lips stand out more and highlight them. Then we apply bilateral filtering to smooth the image even more, but it preserves the edges. And then we sharpen the image to accentuate the edges of the lips. And basically, all my pre-processing done is just to make the lips more obvious and more distinguished so that the model can pick up on little details easier. And on the right, here are a few of the video clips that is from my training data. So for my data set in total, I have around 681 video clips of words being spoken. Each word has around 50 different data counts. As you can see, the distributions on the right. The final data set is 3 gigabytes worth of a NumPy array, and that's the dimension 681 by 22 by 80 by 112 by 3, which results in around 400 million values. The reason why we have this dimension is we have 681 video clips. For each video clip, it has 22 frames. For each frame, the dimensions of that frame is 80 by 112 pixels. And for each pixel, we have 3 different RGB channels. This dataset was then split into 80% training and 20% testing. And for the training environment, I used Kaggle since it has free accelerators, and the one I used was a P100 GPU. However, the problem with Kaggle is that it had a RAM limitation of around 16 gigabytes, which is pretty small, and this meant that after running my model a singular time, I would have to reset the entire kernel to clear the RAM. And this definitely was very time consuming and unfortunate. So for the model itself, I'll briefly go over the architecture that I stuck with. We start off with 3 conv 3D layers, and each layer has ReLU as an activation function. After each conv 3D layer, we follow with max pooling 3D layers, except for the last one. And this is just to downsample the image or video, I guess. Following that, we flatten the model, then we add 3 dense layers, which are fully connected, and these also have ReLU activation functions. We prevent overfitting in this model by adding L2 regularization to each layer. So both conv3D and dense layers have this regularization. I think the alpha value I chose was around 0.001. And we also have dropout layers after the dense layers of 0.5, which means we're dropping out half the nodes after each dense layer, so that the model does not rely on a singular node or group of nodes too much. The optimizer I chose was Adam, since I think by default, Adam is a very strong optimizer, and it definitely worked well in my case. And since we are doing categorical classification, the loss was categorical cross entropy. So now let's talk about the results. On the right is the graphs of my epochs. which I trained over 20 epochs with a batch size of 16. In the end, as you can see, the model is able to converge well and have a final training accuracy of 95.7% and a final testing accuracy of 98.5%. And these values are very high, which indicates that my model can perform well on unseen data. Below, we have a confusion matrix. And in this confusion matrix for this model, we basically see that we can classify everything correctly, except for one instance of an A with a cat. And as I mentioned before, A, cat have similar lip movements. And I've also seen this trend in different models and confusion matrices where similar lip movement words are classified wrong the most often. Here's a continuation of my results. So for each class, I also calculate the precision, the recall, and the F1 score. And they're essentially all one, which indicates that my model has a high true positive rate and a low false positive rate. And this can be shown even more with the figure on the right, where I graphed the ROC curve and calculate the AUC values. The AUC values, like the previous metrics, are all basically very high. And this indicates that my model has excellent discriminatory power. And then the ROC curve shows a steep rise on the top left corner, which indicates the model has like a high true positive rate at a very low false positive rate. And that's exactly what we need and want inside one of these models. So some discussion. Future improvements include definitely getting more data and ideally data from more faces and different people, since this will allow my model to generalize well to new faces or unseen faces. I definitely like more processing power since having no RAM limitations will allow me to experiment with more models and do more hyperparameter tuning. I can also test out different architectures, and this includes maybe using LSTMs or gated recurrent units. For this model, or for this project specifically, I found that I didn't need that since I guess the video clips were short enough. But for maybe like if I were to classify different phrases or longer video clips, this might be useful. And then for related work, I wanted to talk about like the topic of classification using 3D CNNs. It's definitely not a novel idea and has been done before a lot of times. And for example, in this research paper here, they used 3D CNNs to classify human movements into categories of actions. And their research achieves an accuracy of 98% approximately, which just shows that 3D CNNs are a good good solution to this type of task. Yeah, so that's basically it for my project. I think overall, I was able to prove that using 3D CNNs, we can classify lip movements into words pretty accurately, and it's definitely a viable technique. If you have any questions, please let me know, and thank you very much for watching.